Excellent. So, do y'all have any questions on anything? We got that web work floating around. Does anybody need any help with that one? That improper integrals one? Are you looking to see? Is that a no? You're good.
No, I'm good.
Okay, awesome, cool. I thought you were like getting a problem there. Awesome, cool. This is one of the funnest things I think in Calc 3. One of them, and we are going to look at solids of revolution. Really fun application of the integral and of the Riemann sum, and we're going to use Riemann sums to develop some formulas and understanding for ourselves. So let's talk about the basic problem at hand. I've got some function y equals f of x, and I've got it on some interval a to b. I'm going to spin this around. I kind of hinted that we're going to do this. I'm going to spin this around the x-axis, and then later we'll spin it around the y-axis also. But we're going to spin that curve, in fact, this entire region here, around the x-axis. And when we do that, we're going to produce a solid. So just imagine, you know those decorations you get out on the table, like at Thanksgiving, and they spread open, and they're like accordions. So that's basically what's going to happen here, except it's going to be a nice solid thing. So we're going to spin or revolve about the x-axis. And when I do that, I am going to get a solid that looks something like this. Here's the axis. This is the x-axis, the radial axis. And in the back here, we can't really see it, but there's a hidden flat side back there. And then this comes through and comes out over there. So you can imagine it's actually kind of coming out of the back there. I don't know, this probably doesn't help. So let me get that stuff out of there. Yeah, that looks better. And then just do a little shading here. You see the problem at hand? The visualization's working for you? Cool. And Kellen, you're good on the visualizing. Okay, awesome. Sometimes that's the part people have trouble with. So we want to find a volume formula for this thing. And here's how we're going to do it. We're going to do very calculus-y things. Step one is we're going to partition. Now, this isn't how you'll do it, but we're going to develop the formula. Partition the interval a to b into n subintervals. So I'm going to cut this thing up, little pieces, dot, dot, dot. We're going to call that x0 is a, this is x1, x2, x3, dot, dot, dot. This is going to be x sub n, and then this is x sub n minus 1. And then there's a lot of stuff that can happen between those two. So what we're going to do next, and let's do the interval here. So a is equal to x naught, that is less than x1, less than x2, less than dot, 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 less than x sub n, which is the right endpoint. This produces these subintervals, and you've seen this story before, and you're going to see it again. Step two is in each subinterval. This is kind of one of the things I want you to get out of this class, understanding this process. In each subinterval, choose an x sub I star, and that's going to be between x sub I minus 1 and x sub I in that open interval there. No, actually, it could be closed as well. Could be one of the endpoints. Let me stop. Does this, no, have we talked about this? This just means in. Sorry, I'm getting a little too mathy and not in, just having fun. So this just means in or element of. And I'm talking about the little closed intervals. So picture-wise, if this is x sub I minus 1, and this is x sub I, from my cuts, then I can pick any representative I want in there. And that's what I'm going to do. I'm going to use that representative to make a rectangle, height of which is determined by the value of the function here. So at that interval, I'll just do the picture right here, step 3. So create a rectangle above each subinterval of height, how about we say above the ith? Hello. Subinterval, I'm glad you're here. Above the ith subinterval of height f of x sub I star and width, the width of the subinterval. And that I'm going to denote as delta x sub I equals x sub I minus x sub I minus 1. All right, let me stop there. Make sure, kind of catch up. I'm going to give these two a second to catch up. They're coming into the middle of a lot of notation, so it's a little intense. Just make sure you're following and you understand the process. The notation is to help express some ideas. You don't have to reproduce that as long as you can read it. You know what I'm doing. So in other words, what I'm going to do above the ith subintervals, I'm going to make a rectangle whose height is going to be f of x sub I star and whose width is the subinterval width. And we're going to do that above each subinterval. And what this is going to turn into then, so after we do that, we have, bless you, we have a picture that looks like this. Here's A again, here's B. And I'm going to have a bunch of rectangles. And they can be all sorts of different widths and heights, and that's okay. This whole process works out. Let's see, I'm going to do that from there. Make a really super weird big one. Don't usually do that. And then one last one here. So here you can actually tell. In this example, we have 1, 2, 3, 4, 5. So here n equals 5. This is x sub 1 star, x sub 2 star, on down the ways. So I'm basically it's like we were doing the area of it almost, right? This is basically how you would find the area of this thing, but we're not going to stop there. Now we're going to spin this around and see what we get. So when I spin my new rectangular approximation of that region, so spin about the x-axis, what I'm going to get is a thing that looks like this. It's a stack of coins or discs. It's going to look like a little birthday cake on its side. Next one's not too much bigger. Okay, perspective's getting a little weird. I'm gonna do this all the way because I'm just gonna be a freak and do it. So that's a little too big there, but then this one kind of comes out this, and then I got this last little birthday cake base here. So I get that. And here's the axis that I rotated around. That's still the x-axis. Comes out this side. Sound good? Following? We're going to figure out what the volume of this is. And that's going to be an easier problem because we can work with the volume of a disk. So now we're going to step 4, find the volume of the stacked, and stacked is a loose term because they're side by side, the stacked disks. So let's take a look at one disk. And if we can find the volume of one disk, we're just going to add them all up. So consider for a minute just one disk. the width of that disk is this thing right here. So the width of that disk is delta x of I. The radius of that disk is the height of the function at our representative point. So that's the R. We kind of got what we need now. If I have a disk of radius R and height h, anyone care to guess the volume of it?
Pi r squared h.
Oh, damn, that's good. Yeah, you did the surface area times the height. Perfect. Beautiful, PK. So this is just pi r squared, that's the area of the circle, times the height. You can do that, honestly, with all sorts of shapes. If you just have a thing that is a stack of a certain kind of shape, if you knew this area of this triangle, and then you stacked a bunch of them, it's kind of a good fact to know. I think it's called, oh, the name's escaping me of who it is. It's some chemist, I think. But we've got this little stack of cheese here of height h. Then the volume of this is just the surface area times h. And that's what PK's kind of intuitively knowing. So the volume of the ith disk, is, I'm going to put V sub I equals pi radius squared times the height, which is delta x sub I. Let me know how that feels, because I'm going to add them up. So now let's add these all up. So this volume here, total volume using n disks is going to equal the sum from I equals 1 to n of the volumes of the disks. So I'll just use that notation. This is, did I label it up? Yeah, right here. Okay, cool. There it is. There's the V sub I. And that looks like this. Pi f of x sub I star squared delta x sub I. Almost done. So now the calculus is in. This is how you would approximate that. This is actually how the Babylonians did it. The Babylonians we've seen their computations where they would take like a boat and they would figure the volume of the boat by cutting it into a finite number of pieces, each of which they knew how to find the volume of. And then they added those up, and the more pieces they had, the better the approximation. This is an ancient idea. This is part of our humanity. So this is the approximation. Let's put approximate here, just based on n cuts. What happens if I do this? Limit as n goes to infinity of that quantity. What happens if I let the number of cuts go to infinity? What do we get? What does that turn into? It's a Riemann sum. What do these things become? It's like a thing we do every day in here. What's the one math thing we do every day in here?
Integral?
Integrals, yes! It becomes an integral. So this, provided the function f is nice, and it will always be nice for us. Nice means not too discontinuous, which is a very vague thing to say. So this is equal to the integral of the x slice range times pi f of x squared dx. The little delta x turns into dx, the x sub i's turn into regular x, and I've got this. So we got our first formula. Our first formula is that the volume of the thing we hello, hi. The volume of the thing we spun around the x-axis is equal to pi integral a to b f of x squared dx. Now let's use it. Excuse me, yeah, squared. So let's put this to use. There was a lot of overhead here. You're gonna wanna go back and watch this for sure.
Yeah, that's fine.
So, find the volume of the resulting solid. Ooh, let's do some, oh shit, let's develop a formula. Let's just take a line. So this is just y equals mx. Good old diagonal line, y-intercept 0. I'm gonna take that from, let's say, 0 to, oh hell, let's just make that a 10 right there. And, you know, shit, we'll make it solid. I'm getting a little too crazy. I'm getting a little excited. We'll make that 2x. Just to make things fixed so we don't have too many more variables floating around. So that would make this point here 20. We don't necessarily need that, but we're gonna note it. All right, so I'm gonna spin this around the x-axis. The way to think about these problems is to think about how you're slicing and what the resulting slices look like. Because this is the beginning of this process. We will not be done today. So watch what I'm doing. I'm thinking I'm gonna slice along the x-axis. That means I'm gonna have vertical things that look like this. I would recommend even drawing them in the shape you're rotating. When I spin that little rectangle around the x-axis, it turns into a disk. That's how I know this is the right formula. So a spun slice turns into a disk. And that means we're going to use this formula. So use the disk formula. Now I'm spelling disk in all sorts of ways. I don't know, sure, there's a good disk. So use the disk formula. Right over there. I'm not going to write it out again. I'm going to fill it in. The volume is the integral over the range of cuts. So I'm cutting from 0 to 10. Pi can go out in front. The function itself, this is f of x. That's what determines the height of a slice. So we have 2x quantity squared dx. And if we work that through, we get the volume. What is the shape? What does the resulting shape look like when I spin that line around the x-axis? Cone, yeah, it's a beautiful cone. Yeah, so this is equal to the volume of that lovely cone that we will get when we spin around the x-axis. Let's just do it. You know, this is easy, right? This is like, after all the stuff you guys have been through, this is refreshing. This is an after dinner mint. So we've got pi. I'm gonna actually rework this. I'm gonna pull 2 squared out in front. 0 to 10, x squared dx. Power rule, 4 pi times x cubed over 3. From 0 to 10, the 0 will produce a 0. I put in the 10, that's going to be 1,000, so 4,000 pi thirds units cubed. That's cool. It's cool that we can just build that with our ideas. Now we know how to find the volume of this. And if you wanted, you know, you could even construct formulas for yourself. You could say, oh, I've got a cone of base radius r with a height of h. What's its volume? We could work that out using this method. All right. Any questions on that? Because I'm going to ask you to do one for me. I'm going to make yours way more fun. Don't worry. You're about to have one of the greatest times you've had this week. I kind of hope not. kind of hope there's been some other stuff going on in your life. But this is a cool highlight of your week, for sure. So do the same thing. Find, I'm going to ask you to do this, the volume of the resulting solid. That's gonna always be the question for the next week, probably. Resulting solid, when we rotate, y equals 1 over x, and x is going to run from 1 to infinity around the x-axis. I've kind of alluded to this about the x-axis. So let me help you out, and then you get to do the fun part. Here's 1 over x. That goes on forever and ever. We're about to find the volume of this infinite horn right here. This is sometimes called the Gabriel's horn. So like I guess if you're an angel, your horn is infinitely long, you know? That's just the fun name of this particular example. What is the volume of it? So that's your job. Go forth and conquer. The answer will be pretty. Very pretty answer. Let's get that integral set up and then make sure we're on the same page before we evaluate it. So you kind of got here for the good part, Jose. I mean, you got here for the formula, and you'll get to see me develop similar ones to this today. So you'll get that rib, because this is all, a lot of this is about that getting the formula. That's what we want to understand.
Okay.
And putting little discs in there. Right now you know that this is the kind of rectangle I'm thinking of, and that's going to turn into a disc. But maybe get used to drawing them. Thinking about it. Just getting your mind in that space. Just make sure you agree with that integral. Cool. Cool. You guys good? Yeah. How do we know this integral even converges before we go ahead with it? Does it look like something? Ooh. Looks like this. What's our P? This integral. 2. Yep. And that is bigger than 1, so this integral converges. So we're good. We know that we expect a finite value. A little sanity check, going back, you know, some of the ideas we've been talking about.
this? Do you want a little more time to keep working? Which one is that for?
You're gonna keep going.
Should I explain it? Or good, you want to keep working a little bit? Is that what you're saying?
Or you can explain it.
No, it's a choice. If you want a little more time, let's wait.
Oh, no, I understand what you
Oh, okay, cool. Did you get a final answer?
Oh. Just one.
Yeah. Yes, times pi.
Oh.
Yeah, exactly. Pi units cubed, which is so cool. This is crazy. Does this sound good? Anybody want me to explain any of this? Because I'm going to make it worse. Just a second. Okay. So, let's make it worse. Let's cut some stuff out of it. Now, honestly, what we just did was the hardest part. I don't need to go through. The whole derivation again. But let's do a different one here. So find the volume when we rotate the region bounded by. So now it's getting a little fancier. Region bounded by y equals 2x. Let's just go back to that one. So I'm going to start drawing this out. So y equals 2x is this line. Y equals 2 minus x, which is this line. I'm not quite sure where those intersect. We'll figure it out. If we need to, yeah, we probably need to. And then x equals 2. And that's it. Let's just stop that. And x equals 2. So the region bounded by those three curves. Let's just stop there. In other words, this region right here. So I'm going to spin that little triangle around the x-axis. And I'm going to get the resulting volume. And what's that shape going to look like? Well, it's kind of going to be a washer with a sharp edge and a triangular structure. So it kind of looks like a gasket. A lot of the stuff we're going to look at looks like a gasket. And there's this inner part that's cut out, but these actually come together right at the center, right? So there's like a little V cut out, and then there's this sharp edge. So it kind of looks like a dog bowl.
That's what I was thinking.
What's that?
That's what I was
Is that what you're thinking? Yeah. It's totally like a terrible dog bowl because it's got this conical cut out of the middle. But if I drew, here's my radial axis. Do you kind of see do you see the shape? That's the hard part. Like this is what people have trouble with often, is getting that shape. So, all we really need to do is figure out, now we're going to rotate around the x-axis. And so I'm going to draw a rectangular element in here just so I can help myself think. And I'm going to say, okay, that's at some x coordinate. And I've got that rectangle. I just need to figure out how high that is. And we're going to, and then I also need to figure out how high this bottom part is. So what we're going to do is think of it this way. We're going to first figure out what that point is. We know where we end, so this is our start. This is our end. We got the end, it's 2. Start equals whatever that's at. And we're going to take slices from the start to the end. We're going to think of this as a 2-part process. Really what I'm going to think about is I've got this outer shape that if I didn't have this center here, if I didn't have that there, I would have this rectangle here. So I'm going to think of this volume as this shape, that region there, So this is y equals 2x. This is the x-axis. This is our start, this is our end. And I'm going to subtract off this inner region here, which is this little triangle like this. And this is the x-axis here. And this is y equals 2 minus x on top. So I'm going to spin that thing around, get its volume, spin that thing around, get its volume, and remove it from the bigger volume. Does this make sense? No.
I don't even see the dog hole.
Oh, okay, cool. Shit, let's see here. Okay. Oh, here, I think I can help. I think we can help. Okay, so this shape, kind of this triangle, right?
Yeah.
So imagine now I'm going to rotate this around. Think of what it's tracing out. So taking this little triangle and just spinning it around like, does somebody have tape? I cannot fucking get this thing to like,
I just see it coming, but that's it.
okay, so, but I'm spinning it around a central point. Hold on.
I think I'm being visually challenged.
It's okay, here we go, we got this, we're gonna do this, I think this is gonna help. Hold on. Do a little origami, everything will be better. Sure, that'll work. That kind of looks like that.
Yes.
Okay, thank goodness. All right, so now let's do it on the table here. Because I'm going to keep this corner, so the x-axis is right here, coming straight up this way. So, in other words, I've got this, I'm just bringing it down to the table, like that. Now I'm going to spin this thing around that central axis. Do you see the shape? Does that, I can't get that fucking pen to stay still. There we go. Oh, look at that.
Oh, okay.
These are slices of the bowl.
I see.
Do you see? Does that help? Yeah? Except that the bowl is on its side, right? So the bowl is actually,
Oh, okay.
yeah?
Okay.
Cool. Okay, cool. I'll do whatever it takes. Whatever it takes. So, do we see that this bowl, to build this bowl, I could first take whatever this shape produces. Let's spin that around. So when you take that shape and you spin it around, you get what's called a frustrum. And this looks like a little platform. So this is actually solid. If I take that and I spin it around the x-axis, I get this frustrum. Does that make sense, taking that piece there and just spinning it? Just this piece.
Where do you get the piece from? Sorry.
That's okay. No, I'm glad you're asking. It's this bigger piece right here.
Oh, okay.
Yeah, you see?
Yeah.
So I took that here. And then when I talk about the little piece, you see, it's this one here.
Okay.
Okay, cool. So we're going to take this volume, this bigger volume produced by this spinning, and remove this inner volume. Now this inner one's going to look like a cone. Does that make sense if I just take this little thing right here that I just colored in and I spin that around the x-axis? That's a literal cone. And so then I'm going to subtract that cone from this bowl. So we're going to find this volume minus this volume. So I'm going to remove this chunk of material from this thing. So the way to find the resulting volume is to find the volume of the bigger thing minus the volume of the little thing. And that's it. Let's think about how that might look. And honestly, like getting these, like practicing your visualization is gonna be super helpful here. So first off, we need to find that intersection point. Intersection. And we had y equals 2x and y equals 2 minus x, and I'm kind of excited to see what these are. So I'm going to set those equal. Set that equal to 2 minus x. That's 3x equals 2. That's x equals 2/3. So that is this point right here. And then we end at 2. We were given the end slice right there. So now I'm going to go through here, and I want you to think about what I'm saying, because I think you're going to hear me say this 1,000 times. I'm going to take outer and then minus inner. Now I'm going to do this in 2 parts, but always think outer minus inner, upper minus lower, right minus left. So for us, outer is always going to be a further away, either up or this way, and inner is going to be closer to the axes, either this way or this way. So what we're going to do here is we're going to say the volume is equal to the outer volume minus the inner volume. I've kind of been saying that, but now I'm going to write it up there. So the outer volume is going to be pi integral from 2/3 to 2. I'm thinking about how do my slices run? And they start at 2/3 and they end at 2. From 2/3 to 2. What is the outer curve? It's the 2x curve here. So the 2x is on the outer edge. So I'm going to put here 2x squared. And then I'm going to put dx here. So this is actually the volume of that frustrum here, that solid frustrum. And then I'm going to subtract off integral 2/3 to 2 of that inner cone, this little cone right here. And how high are the elements in that? They are 2 minus x units high. So here I have 2 minus x quantity squared dx. That's it. I can make this look a little bit better. Notice that the bounds on these there's a pi here, there's 2/3 to 2, 2/3 to 2. Let's write the whole thing together as pi integral from 2/3 to 2 outer radius squared minus inner radius squared. So I'm going to write this formula up in a new way. We don't even care. We don't even give a shit what that actual number is. And we're not going to for most of our problems. I want you to set these up, and that's going to be the hard part. So you're now going to communicate in integrals. We'll do some... Yes, you are. Yes, you are. And you'll be happy. I'm going to do some written homework. You'll be relieved of the suffrage of web work for a short while. You will pay dearly for it. So let's just look at a quick summary here. Sorry, guys. Find the volume of resulting solid. And here we're rotating about x axis. So drawing a picture, let's say I've got my f of x here, I've got my g of x down here, and maybe I'm integrating from a to b. So I'm taking that weird ass region, spinning that around the x-axis, and good lord, drawing that one is kind of tough. The outside is going to look like a bell because of that outer edge. The inside I can't even draw, right? But there is an open top here. This thing actually has a hole through the center, and you can kind of imagine what like a little slice of it looks like. Kind of like that. But there is this open top here. How's that one working for you, Yuski?
That's getting
It's getting there, cool, awesome, you're getting stronger, man, I feel it. So we're gonna, if I want this, what I'm gonna do is I'm going to integrate, I'm gonna take pi times the integral of the start slice to the end slice. And here that's a to b. And I'm gonna have my outer function, and here that's f of x, squared minus inner function squared dx. Using the notation I've set up. I like this because this is the intuitive understanding you're gonna want when you set these things up. So, or pi integral a to b f of x squared minus g of x squared dx. But thinking in terms of outer and inner is gonna make this so much easier for you, I promise. Been teaching this kind of like this for like 20 years, and I think this works pretty good. You guys trust, I think you trust me. You know I'll take care of you. And you know if you don't understand, I got you. We'll get there. All right, so let me give you one. All right, so give you a nice one. This is chill. Let's just take y equals x squared. Yay. Don't do the integral, just set up the volume integral. And we're going to remove y equals x cubed. So here, the squared is on top because this point is 1, and this point is cubed. Can you find the volume of this region rotated from 0 to 1? So the region is, the x range is 0 to 1, and between y equals x squared and y equals x cubed. Can you set up that integral, please? And then if you get bored because you're like, man, this is going slow, I gotta do an integral, crank out the integral. Take an element, right? You need to know outer and inner. And I'll have fun, I'll entertain myself while trying to draw this out. Kind of looks like the end of a trumpet, just all sealed off on the end there. Wow, that's cool. I'll do a little simplify. Oh hell, and I'm gonna work it through while you guys are still working on it, because calculus. Why not? Why wouldn't I do calculus? So let's get to a place where we feel like we understand how to get there. And then we're gonna make it harder. But better. And it'll still be the same. You're gonna see that this is all the same thought process over and over again. I'm just being a wanker by saying it is harder. Set up. Yes, sir.
Will the answer always be positive?
Yes, good sanity check. Yeah, absolutely. If you got a negative, you probably took inside minus outside. Is that what happened? Oh no, Othman.
Oh.
Did you do it backwards and get a negative or?
No, I
Okay.
got it.
Oh, cool. I just saw a smile. I thought you were like, that's exactly. Is that what happened for you, Jose?
No.
Okay,
No, I was
just
just
checking.
I was just checking out.
Yeah, that's a good thing to observe. Yeah, absolutely. Always positive. Any other questions on that? Because now I want to rotate around something besides the x-axis. Like, that's so freaking boring. We don't want to do that. So what we're going to do is this. We're going to take another region that maybe is defined by two different curves. Well, actually, here, let's go down here. We'll start a little chiller. Little bit chiller. So let's say I've got y equals f of x here. And I'm going to do that from A to B. But I'm not spinning around this axis. Now I'm spinning around that line y equals L. That's going to be my axis. So instead of spinning here and getting that like vase, the vase shape I would get here, I'm going to spin around here and get a different vase around it. So now we're going to spin around that axis. Yeah, and it's going to look vase-like, right? It's still going to be vase-like, except we're going to have this vase floating up here, kind of like something like that. Something like that. Yeah, something like that. Not exactly that. I think this lip is a little more sharp there. All right, so same game. Same dang game. Except for one difference. What we're gonna do, of course, is we're gonna spin elements that look like that around. Now think of how you get to that element. It's actually the difference of two elements. Let me get another color pen up here. A couple of different colors. So if I spin this element, just basically all the way down to here, around this axis, what does this red thing turn into if I spin it around this axis? Coin, yeah, I like that, coin. Yeah, we get a disc. We get a disc if I spin that red thing around. If I subtract off this volume down here, wait, I gotta make sure I'm doing this right. Yeah, that would be good. If I subtract off, so if you took this whole thing and you spun it around, and then you subtracted off the area resulting, the volume resulting by this little piece here. So like if I took all these pieces here, sorry, I'm not explaining this well. Let me draw a picture, because those seem to be working fairly well, a little bit better. So the volume that I want is that thing. That volume is the difference between the disc I get, excuse me, just the cylinder I get when I spin this red element around my axis. So this is y equals L, right here. This actually is the x-axis down here, and it's getting spun around that thing. Then I'm gonna carve this thing out. I'm actually gonna remove the volume that I get when I spin this thing around. So minus this volume here, which is, no, that isn't what, okay, so give me a second. I got myself a little confused here. All right, let's see, what am I doing? Good spin. Oh, okay, what am I doing? I need to just think. I need to think instead of thinking about what I've done before. Let me think fresh. Our elements are gonna look like this. Okay, here we go. I got it now. I'm better. Instantly better, because I just had to start thinking about the process. So like, don't memorize these formulas, even though you could write them on a sheet and have that sheet next to you. I know no one in here will do that, because we don't roll that way. We don't roll with reference sheets. You got it there? Was it open? There you go. Look at you. Thank you, sir. Thank you, sir. So now my sarcasm just is not quite hitting fully. All right. So we're going to take this element here and spin it around. And when we get that, we're going to get another stack of coins, right? We're going to get another little stack of coins. I'm going to spare you watching me do these little stacks of coins all the way across, even though I don't seem to be sparing you anything. I kind of just seem to keep doing it. So anyway, some weird little Michelin man appearing here. But I'm going to spin that thing around. So think about how do you do that? You've got a series of discs that we're going to add up the volumes of, right? This just turns into a series of discs. We'll add them up. So what is going to be the volume of one of those discs at an arbitrary slice? So we're going to pick X, and we're going to figure out what is the radius of that sucker there. Here we go. Okay. Whew. Got my bearings back. Having that picture is all you freaking need. Because if this is y equals f of x, what is the length of that radius right there? So what's the length of that long line I've drawn? So far away. So hopefully you can tell me by the time I get over there and get my tea.
Would it just be the formula of the volume times half?
Where'd you come up with the half? I'm interested. That's not the right answer, but I'm curious how you came up with it.
Well, I was thinking about like the diameter.
Thinking about what?
Diameter.
Oh, diameter. Yeah.
Which is, since radius is like the half of it.
Oh, okay. Yes. You're thinking good, but not specific enough to this situation.
Okay.
How could I find how high this line is here? Vincent can help me. Vincent, how high is that line?
Which one?
This one right here. This little radius here. So this is y equals L.
Yeah.
And then this is y equals f of x right here. And we're at the point x here. So how long is that radius on that disk?
2fx.
Or
like 2y, like it'd be twice.
No, there's two. there's no twos in this. We're getting a lot of two thoughts.
Is it L minus f of x?
There we go, thank you. Does that make sense now? Because you probably didn't even know exactly what I was asking,
Yeah.
so, yeah. Do we see that?
No.
Okay, good.
So is it, in this case, it's, oh wait, no, never mind, I see it.
You see it?
Yeah.
Cool, so, this segment right here, PK, how long is it? Well, look at the distance from where it's touching here to the x-axis. This distance here is L, because that line is L units high. And then we just subtract off f of x, this height right here.
Oh.
It's tricky, I almost got myself confused
So
there.
yeah, in this case, instead of doing like, outer minus inner, you're doing,
Top minus bottom.
yeah,
Yeah.
okay. Which the bottom is the outer, in this case.
Yes, yeah.
Alright.
Is this good? All right, so this is the radius of the xth disk, the disk right above any coordinate x. And now it's just the volume of this thing is going to be, the volume of this little disk is going to be pi times its radius squared times its thickness. And its thickness is, you're always going to use delta x for the thickness. That's the cut size down here. So this is going to equal pi times our radius, which is L minus f of x quantity squared dx, or delta x, excuse me. Delta x, I haven't gone to the integral yet. And I add those all up. And if I add up all those little volumes, it's going to turn into, eventually, when I let the number of slices go to infinity, pi integral of L minus f of x quantity squared dx. So let's do an example. Exactly. Exactly, PK. I think that was you. Yes. That was you're very compact. I like your note system. It's just like, it's a man of a minimalist. This man is a minimalist. Travel light, right? Travel light. All right, so we get a better pen. Oh, these all suck. Whatever, we'll just stick with this one. So find the volume. Find the volume. We're gonna rotate y equals x squared about y equals 1 from x equals 1 to x equals 2. Draw the picture. Y equals x squared. X equals 1. X equals 2. Pick them wherever you want. It's up to you. And then the line y equals 1 is right there. So, yeah, so I didn't quite say that, yeah. And so this is the region I want right here. So let me say it a little bit better. Volume from rotating yeah. Rotating this region R, let's call it R right here, about y equals 1. And so the answer is just going to be, look at a slice. You're slicing this way, so I take my arbitrary slice. Those slices run from 1 to 2. So that's how I set up my integral bounds. What are my slices running between and 2? Definitely got that pi out in front. And then I've got the top minus the bottom. I'm going to square that dx. And what we've done
just spinning around this, and we're actually gonna get this little, again, the same shape, the same damn shape we've been getting the whole day. Like this.
Except it's now above at a different axis. Let's try another one. I think I might, over the break, you know, we don't meet on Monday or Wednesday, Friday or Monday, right? Everybody knows that. I'm gonna record a little video of just some examples of working this stuff through so you have them. I'm not even gonna give you a new assignment yet. You've got to just finish up finish up what you got so we can come back and have a nice fresh start. This is kind of warming you up for next week. You okay?
Huh?
Are you okay?
Yeah,
Okay.
and just allergies.
Okay, cool. Yeah, and if you were actually upset, what a terrible thing for me to say right in front of the whole fucking class. So, I'm glad it's just your allergies. Okay, cool. All right, let's do one more here. Oh, could you take that region and spin it around the x-axis and tell me what you get, please? Let's do that one. So this was about y equals 1. Now rotate it r about the x-axis. I want you to do two things here. Give me the volume and give me the shape. What does it look like? Take them here. We'll see a different formula, but let's see that formula together. This is good. This is good practice. You working on these visualizations. Jose, just really quick, one time, something you said a little earlier on this. This is, notice that this is actually also outer minus inner, kind of, right? Because the outer one was this guy. And
Yeah,
then,
I
okay,
realized
cool.
that, so I switched it over.
Awesome.
I just put top and bottom.
That's a better way to think of it, yeah. And the formula is going to look really similar, but it's not the same thing. I'm going to work this one through so we can get that volume. I would expect the volume we get here to be bigger, I think. I think it'll be a bigger volume. It just seems like more stuff. I'll work this through. Oh, I wish I hadn't done this. There's no way I'm going to simplify this. Oh shit, I'll do it. Thank you. Thank you, sir. Yeah, I was joking on that. Awesome. Thanks.
Oh wait, no, but
Oh, yeah.
I had the
Oh,
15.
gotcha. So 32.
30.
Gotcha.
Yeah,
Awesome.
32.
Thank you.
I just saw you pointing at that.
Yeah, you were right. Yeah, you're absolutely right. That's units cubed. Cool. Can anybody help us out with that one? Anybody feel confident enough to give that volume formula up there?
Cause you're just doing the x squared integral over 2 to 1, like a 159 pi over 5.
Yeah, you also have to subtract out the integral of 1 from 1 to 2, because you're taking out this little cylinder in the center. So you have, does that make sense?
So I just got the whole thing, I just need to subtract it by.
Exactly.
Okay.
Yeah, you got it as if we were just doing this whole region here, as opposed to that. So, I mean, one thing to do is just think outer volume minus inner volume. So our volume is going to be pi integral 1 to 2 of x squared squared. And I think that's what you just said. I think you did, right? You did this.
Yeah.
Yes. And then we just want to subtract off that inner radius squared. Like that. And so that would be the volume we're looking for right now. Notice it kind of looks similar, but only similar in the mind of a person whose math skills are not super great. So what happens, this happens so much. People take this square and just like, la 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 la. That's called the freshman's dream in math teacher circles. That's the freshman's dream. That is not true. So these two are not the same. This is pi integral 1 to 2. We'll call it after this. X to the 4th minus 1 dx. I want to see, honestly, I kind of want to see how the volumes compare. So this is pi 1/5 x to the 5th minus x 1 to 2. Okay, we've done worse. We just did worse. So this is pi 32/5 minus 2 minus 1/5 plus 1. And so then what do we got here? Again, 31/5. Oh, that's cool. Look at that. Look at that. There's 31/5. And there's the minus 1. Is that right? Did I get that right? Yeah. Okay, yeah. It's a little different for sure. So then that is 26/5. 26/5. Pi. Huh. This looks bigger. I don't know. Which one's, but can we actually get some calculator action here? And just get some approximates here. So this is approximately, please do the pi times. Seven-ish. For which one? This guy, either one, just give me whichever one you just
For
did.
that one, I got 16.34.
And then what we got on this guy?
6.7.
6.7. That was close. 6.7. Significantly more volume, almost 3 times more, somewhere between 2 and 3 times more volume. Yeah, more like 2 times. Anyway, welcome to your life for the next week.
So the one on the top, you did rotating around the x-axis. So there's the center area that's missing.
Yes.
It's
It's like hollow.
Perfect. It's hollow. Yeah, exactly.
I can't imagine the area being different though. I don't know why.
It's strange, right? But this one, I mean, it looks like it's more of a gasket, right? It looks like this, and then these sides are flat in here. Right? So there's kind of this cylinder just cut out of the center.
Yeah.
Whereas the other one is really just a very solid cone thing that is actually, oh, here, this might, can't draw them next to each
Because
other.
the distance between the x-axis is so much larger.
Yes.
Okay.
Yeah, it's when you get, the further out you move away and rotate,
gonna
you
be
just,
bigger,
yeah,
yeah.
exactly.
Okay.
Yeah. Just think about how the circumference here changes. It's
Yeah.
pretty significant, yeah. Okay. Yeah, cool. Great questions. Good stuff, friends. Congratulations, you've made it through half a semester of Calc 2. It's all downhill after here, man. We go fast when we get back. I don't mean downhill
Yeah, it sounded bad.
that didn't sound good. Well, your careers are over after this, so enjoy your break. No. We're gonna have fun. I'll make a little video with some examples of this stuff so you have them for reference. But I won't ask you to do anything. I want you to rest a little.